Hello guys, you're all welcome to my YouTube channel, and in today's class we'll be dealing with organic chemistry. So you stay in this class. I'm going to be explaining everything you need to know about organic chemistry in order to pass your JAMB or WAEC or JUPEP exam. So let's get right into the video. So now the first thing you need to know is the definition of organic chemistry. What is organic chemistry? So basically, organic chemistry is the chemistry of compounds of carbon. You understand? When you talk about carbon, if you sit in your JAM exam, what is organic chemistry? You should know that organic chemistry is the type of a chemistry that deals with the compounds of carbon. But here is the catch: it is not all compounds of carbon that we deal with in organic chemistry. We exclude basic oxides, or just say oxides, oxide, and also carbides, and even carbonates, carbonates of carbon. Yeah, you understand? So compounds of carbon that are oxides, carbides, or carbonates, we don't usually refer to them under organic chemistry. I believe you are getting me. An example of an oxide is carbon monoxide or carbon dioxide, carbon monoxide, CO, or carbon dioxide. These two are not organic compounds. You understand? Even carbides, something like calcium carbide, that's I think CaC, yeah, these are not under organic chemistry. Even carbonates, you can have something like CaCO3. That's our normal limestone. So these compounds are not type or they are not under organic chemistry. You understand? So organic chemistry deals with the chemistry of carbon, right? So that's that for that. So there's one thing that we need to know about organic chemistry, and that is what I call the homologous series. Everyone here, if you don't know what homologous series is, let me explain in the best way you understand. Homologous series in organic chemistry is just like families of elements or families of compounds that we classify them together. Just like in real life, in real life, we usually have family, and in a family, there's usually the father, the mother, and the children, the firstborn, and all of those. So that is how it is in organic chemistry. Organic chemistry, we have compounds that look alike. So these compounds that look alike, they form what we call the homologous series. You understand? So when you talk about homologous series, that's when you talk about something like the alkane homologous series. I'm sure many of you must have heard about that. The alkenes, okay, the alkynes. I'm going to explain all of these homologous series in these videos. The alkanol, the alkanol homologous series, the carboxylic acid homologous series, the carboxylic acid homologous series, and even the ketone homologous series, or even the alkanal homologous series. You understand? And even the ester homologous series, and even the ether homologous series. So I'm going to explain all of these homologous series in this particular video. So this video is going to be as detailed as possible. It's going to be long, but I'm going to explain everything you need to know about all of these homologous series. So now there are certain characteristics of elements that belong to the same homologous series. I would love you to know some of these characteristics. So now let us start. Now, each member of an homologous series, they usually differ in CH2. That means that if the first member of an homologous series is, for example, now the alkane series, the first member of the alkane series is methane, which is CH4, right? So the next member of the alkane homologous series is going to be CH4 plus CH2, something like CH4 plus CH2. You understand? And that's going to give us C plus C is what? C2. H4 plus H2 is what? That's H6. This is the next member, and we call this ethane. We call this ethane. You understand what I'm saying? I'm just trying to give you guys an example that each member of an homologous series or successive members of an homologous series differ by CH2. They differ by CH2, or they differ by 14 grams per mole in terms of their atomic mass. You understand? In terms of their atomic mass. Some people might not understand how we got this 14 grams per mole. It is not difficult. It is not difficult. It is just the mass of carbon and the atomic mass of hydrogen. See here, the atomic mass, we all know that the atomic mass of carbon is 12, right? 12 plus the atomic mass of hydrogen is 1. And don't forget that we have two atoms of hydrogen. So we have 2 times 1, that's going to give us 2, right? So 12 plus 2 is what? 14. 14 grams per mole. So this is how we got this 14 grams per mole. So each successive members of an homologous series differ in CH2. Any of these homologous series, successive members of the same homologous series differ in CH2. Right? I believe you've gotten that. You can see it in your JAMB exam. You should get the answer correctly. Right? So another feature of homologous series you need to know is that members of the same homologous series usually experience a change in their physical property. Their physical property as you move down the homologous series. For example, now the boiling point or and melting point of each member of an homologous series increases as you go down the series. You understand? For the first member, it might not be very high for the boiling point, but if you go to the second member, it will get a bit higher, and so on and so forth. So I'm just trying to explain different things about the homologous series that you guys need to know. So basically, that's all about homologous series. And now there's one other thing. Thank God I didn't forget this. Thank you, Holy Spirit. The thing is that each member of an or all the members of an homologous series, they have or they conform to what we call a general formula. They conform to what we call a general formula. That means that all the members in an homologous series have a general formula that they conform to. For example, now the alkane homologous series, they have a general formula, right? The general formula of the alkane homologous series is CnH2n plus 2. I'm still going to explain all of this formula. You understand? I'm just trying to say each member of an homologous series conform to a general formula. This is general formula for alkane. Alkanes, they have their own general formula. Alkynes, they have their own general formula. Alkanol, they have their own general formula. Carboxylic acids, they have their own general formula, and so on. I hope you get this. So that is that for that. So now I want to teach you guys one other thing before we continue, and I don't want you guys to forget this. Now you should not forget that organic chemistry is the chemistry of carbon compounds. Now, carbon, we usually see that carbon usually takes 4 bonds. Carbon usually takes 4 bonds. You understand? Mostly carbon bond covalently. Mostly or most times, carbon likes bonding covalently. So it takes 4 bonds. Now the reason is, why does carbon takes 4 bonds? Let me explain before we continue. After I finish explaining this, we are going to start with the alkane homologous series. And in this class also, we are also going to be dealing with IUPAC nomenclature. I'm going to give you guys examples of IUPAC nomenclature of each of these homologous series, and I'm going to be explaining everything. So stay glued. If you have not subscribed to this YouTube channel, now is the best time to subscribe to this YouTube channel. So now, let me explain why carbon has 4 bonds, or why it takes 4 bonds, or why it bonds covalently 4 times. Now, this is it. Carbon has an atomic number of what? The atomic number of carbon is 6, right? The atomic number of carbon is 6. In a neutral carbon atom, that means that carbon has 6 protons, right? 6 protons, because the atomic number is 6. So because this carbon atom is neutral, right? It will also have 6 electrons. It will also have 6 electrons. People should not forget that when you talk about bonding, or when you talk about bonds, the next thing that you should think about anytime you hear bonds is or are electrons. Bonds deal with electrons. That is when valency comes in. I believe you people know valency, right? If you don't know valency, let me explain now. Valency is what we call the combining power of elements. The combining power of elements. How elements combine together, or the combining power of atoms, right? Hope you guys are following me. So valency is what tells us if an atom can receive electrons, or if an atom can lose electrons to become stable. I believe we all know that all atoms or all elements are looking for stability when they want to bond with another atom, right? So now for carbon has 6 electrons, right? That means that in the first shell of carbon, let us say this is the shell of carbon. This is the first shell. The first shell of carbon, it will have 2 electrons in the first shell. I believe you all know that the maximum number of electrons that can be in the first shell of an atom is 2, right? And in this is the second shell. This is the second shell of carbon. I believe you all know that the maximum number of electrons that can be in the second shell is 8, according to the rule of 2n square. This rule, this 2n square rule, it tells us the number of electrons that can be in a particular shell, in the principal quantum shell. I believe you guys are following me. So now, for the first shell, let me try to give you guys an example why we have two electrons in the first shell, right? This N shows the shell. If it is the first shell, the second shell, the third shell, or the fourth shell, you get what I'm saying, right? So if it is the first shell, N is going to be 1. So if you replace N with 1 for the first shell, you are going to have something like 2 times 1 squared. So 1 squared is 1. So 2 times 1 is going to give you 2. 2 electrons. That is why we only have 2 electrons in the first shell. So in the second shell, if you put 2 in the place of N, 2 times 2 raised power 2. You have 2 raised power 2 is what? 4, right? So we have 2 times 4. So 2 times 4 is 8 electrons. That is why the maximum number of electrons that can be in the second shell is 8. And don't forget that what? Carbon only has 6 electrons, right? And in the first shell, it has already occupied, or it already has 2 in the first shell. So in the second shell, how many will you have? Correct. It will have 4. So 1, 2, 3, 4. So it will have 4 electrons in its second shell, right? So if you're writing the configuration, you can only write 2, 4, right? So you should not forget that in the second shell, it is normally supposed to have 8 electrons. So it remains 4 electrons. This carbon atom needs 4 more electrons to become stable, right? So if it wants to bond with other atoms, or if you want to bond with other elements, it will need to share. It will need to share electrons with other elements by forming 4 different bonds. For example, now in CH4, carbon, one atom of carbon is reacting with 4 atoms of hydrogen, right? So for example, now in this CH4, this is the carbon atom. It's going to bond or share electrons with hydrogen atom. Let me say this is an hydrogen atom. Hydrogen has 1 valence electron, right? So valence, when I say valence electron, I mean electrons that are in the valence shell. When I say the valence shell, I mean the outermost shell. For carbon now, this shell is the valence shell, right? This shell is the valence shell because it is the outermost shell. For hydrogen, atomic number of hydrogen is 1, right? So it has only 1 electron. So it will share this 1 electron with this carbon, and then C. Remember, it is 4 hydrogen atom. This one we also share. This one we also share. We donate 1, and they will share it together. You can see the bonding. This thing that we have here is methane. You see, carbon is bonding covalently with 4 atoms of hydrogen, right? Bonding covalently with 4 atoms of hydrogen, forming 4 bonds. You can see. So basically, that is why carbon has 4 bonds. So that means that carbon cannot take more than 4 bonds. I want you to know this. If you sit in your JAMB exam, that they ask you that how many bonds can carbon take, you should not think about it. Just know, pick your answer 4, and that is it. So I believe that's very simple to understand. So now let us move to the first homologous series. We want to move to the homologous series of the alkanes now. But before then, let me explain another thing that you people need to know. I want to explain the classification of organic compounds based on saturation, and unsaturation, unsaturation, saturation and unsaturation. This is something you guys should understand. Saturated organic compounds and unsaturated organic compounds. When you hear saturated organic compounds are compounds that only possess single bonds, single carbon to carbon bonds, like single carbon to carbon bonds. That is a saturated organic compound. For example, now, methane. This is the structure of methane. Methane is CH4, right? This is the structure. Carbon, singly bond with 4 hydrogen atoms. This is a saturated compound because it only has single bonds. You understand? Or example, ethane. This is the formula of ethane. C2H6. This is the formula of ethane, and this is the structure. You can see they are only single bonds. You see, the carbon to carbon bond is just a single bond. You understand? So that is saturated organic compound. So when you hear about unsaturated organic compound or compounds that are not saturated, they usually have double bonds, carbon to carbon double bonds, or carbon to carbon triple bonds. You understand? So double bonds are usually most times alkenes. Alkenes was alkane homologous series. I'll still explain everything. And triple bond usually attributed to the alkyne homologous series. I hope you guys are following me. So now I want to give you guys just one simple thing about the classification of organic compounds. So now, organic compounds. I was supposed to have explained this from the beginning, but I don't know why it skipped my mind. So organic, let me say organic chemistry. Organic chemistry is divided into four broad aspects. Four broad aspects. And I'm going to be giving you guys the four broad aspects. The first aspect is what we call the aliphatics. The aliphatics, right? The aliphatics. And there's another one that we call the alicyclics. Alicyclics. And the another one we call them the aromatics. The aromatics. And the last one we call them the arenes. The arenes. I'm going to explain everything. Both the aliphatics, the alicyclics, the aromatics, and the arenes. I hope you guys are following me. So now, for the aliphatics are organic compounds that usually possess straight chains or branched chains. When I say straight chain, I mean something like this ethane. This is a straight chain member. You understand? Or branched chain, as in, let me give you an example of a branched chain. A branched chain compound. This is an example of a branched chain compound. Let me say C3H7, right? This is an example of a branched chain compound. You see that this compound is branched chain. This compound is branched chain because it actually has a branch of this C3H7. This C3H7, we usually call it propyl, but I'm still going to explain everything, right? So this is an example of a branched chain. So under the aliphatics, we have the alkane, we have the alkanes, we even have the alkynes. The alkanes, and alkynes. They are all under the aliphatics. So now we have the alicyclics. As you can see, cyclics. These ones they usually have like a circle, or they are usually enclosed together. For example, let me show you an example of an alicyclic. This aliphatic they can be double bond, single bond, or even triple bond. Even alicyclics can be double bond, single bond, or even triple bond. But the thing about alicyclic is that they are in a circular, it's not really circular, but the atoms, or the carbon to carbon atoms, they are joined together. Let me give you an example now. See, this is an example of an alicyclic compound. This is an example of an alicyclic compound, or we call it the cycloaliphatics. You see, this is an example of cyclic compound. You see, and this particular compound is what we call what? We call this the cyclopropane. This is cyclopropane because it actually has three carbons. But I'm still going to explain everything for those that don't understand. But what I'm just trying is to say is that for the early cyclics, they are usually um the they are enclosed. And that's what I'll say. They are enclosed. For example, another example of an alicyclic compound is this. They are usually enclosed. You see that they are closed. You see, you see. This is an example. This is cyclobutane. This is cyclobutane. So it is not always single bond. It can even be double bond or even triple bond. You understand? So that is for alicyclics. So now for aromatics. Aromatics are compounds of benzene. Aromatics are compounds of benzene. And aromatic compounds, they usually have a ring. They usually have a ring. Okay, let me just open another page so that you people will keep following me. So, compounds of benzenes, they are the aromatics. They are the aromatics, right? Compounds of benzene are the aromatics. Firstly, I believe you all know that the formula for benzene is 6686, right? And benzene is always like this. Benzene is always, this is how benzene is. This is benzene. This is benzene. They usually have a ring. But let me try to draw the structure. Let me try to draw the structure so that you will not get lost. So this is usually benzene. This is how benzene is. See, benzene is almost like the alicyclics, but it is because of the resonance structure. You see, I'll show you what I mean by resonance structure. You see, benzene actually has double bonds. You see, it has double bonds. You can see what I'm saying, right? See, this is benzene. This is benzene. So compounds of benzene are the aromatics. If you add other things to benzene, they form the aromatics. I hope you are following me. So this double bond is not stable like this. It can be moving. It can be moving. So it can be moving and be changing position. That's what we call the resonance structure of benzene. And that is why we usually write it in form of a ring like this. Hope you guys are following me. So that's that for the aromatics. So now for the arenes, the arenes, they are very, very simple. The arenes are just like combination of the aromatics and the aliphatic. You understand? For example, now if our benzene combines with methyl, or if it combines with a- ethyl or other aliphatics, you understand? That's when we call it the arenes. So I believe this is very simple to understand. So now let us move to the first homologous series, which is the homologous series of the alkanes. The homologous series of the alkanes. Okay, okay. So now we are moving to the alkane homologous series. So now another name for the alkane homologous series is the paraffin homologous series. Don't forget this, you can be asked in your JAMB exam. So according to what I said earlier, that in each homologous series, that every member of an homologous series conform to a general formula. So the general formula of the alkanes is what we call the CnH2n plus 2. This is the general formula of all the alkanes. That means that each member of the alkanes, all of them, they all conform to this general formula, right? So now let us talk about the members of the alkane homologous series. The first member of the alkane homologous series is methane. Methane. This is the first member, methane, and it has a formula of the formula is CH4, right? This is the formula of methane. And the formula was actually gotten from this general formula. Now, this N in this general formula, it means the number of carbons. The number of carbons. So now, for this methane that is the first member, it has only one carbon. So if you replace N with 1, you are going to be having something like C, N is 1. So C1 or C without anything is still the same thing as C1. So H, so 2 times 1 is what? 2, right? So 2 plus 2 is 4. So that was how methane was gotten, which is the first member. The second member of the alkane homologous series is ethane. Don't forget this, is ethane. And the formula is what? The formula is C2H6. It was actually gotten from this same formula again by just replacing N with 2. You understand? You have something like C, N is 2, right? 2. Then H, so 2 times 2 is what? 4. Then 4 plus 2 is what? 6. So just like that, like that, like that, that's how it goes. So let us keep writing the other one. So after ethane, we have propane. Propane is the next member, and that has the formula of what? C3H8, right? After propane is butane. So I want to write the first 10 members, and the formula is C4H10. You can see that the difference between this, and this is just you are adding CH2 to this to give you this, CH2 from this to give you this, CH2 from this to give you this, just like that, like that, like that, to pentane. Pentane is C5H12. After pentane, we have hexane. Hexane. Hexane is C. Hexane is C6H14, right? After hexane, we have heptane. Heptane is 7, right? So that's C7H16. After heptane, we have octane. Octane is C8H18. After octane, we have nonane. That is 9. Nonane. Nonane. And the formula for nonane is C9H20. After nonane, we have decane. Decane. And the formula for decane is what? C10H22. So that's basically the first 10 members of the alkane series. And one thing you should notice, if you see this alkane series, you see that all of them, they are all ending in ane, which is ANE. So that is the surface of the alkane members. The surface of the alkane member is ane, ANE. They will all end in ANE. So now there is something I need you guys to note. there is a particular group that I want you guys to know because we will need it. And that particular group is what we call the alkyl group. The alkyl group. So now, what is an alkyl group? Alkyl groups are usually gotten from alkane groups because we usually you will be seeing alkyl groups in your naming and even in organic chemistry in general because you need it. So how are alkyl groups gotten? Members of the alkyl groups are gotten when a member of the alkane group loses one hydrogen atom. That is how alkyl groups are gotten. For example, now, if methane loses one hydrogen atom, see, methane is CH4. If it loses one hydrogen atom, it will become what? CH3. This is an alkyl member, and we call it methyl. Methyl. You see the difference? We change this N to what? I. You see, YL, methyl. You understand? So if ethane loses one hydrogen atom, it becomes what? C2H. If it loses one, it will become C2H5. And this we call what? Ethyl. And like that, propane. If propane loses one hydrogen atom, it will become C3H7. And this we call propyl. Right? You can see propyl. This, if butane loses one hydrogen atom, it will become C4H9. And this we call butyl. Right? Butyl. Just like that, like that, like that for everything. It goes like that. Do you understand? So this is basically the trend. You understand? I hope you guys are following me. So now that is for alkanes and alkyl, right? So you should not forget that I said it last time that alkanes are saturated. Alkanes are saturated. Don't forget this. Alkanes are saturated. It is alkanes and alkynes that are unsaturated. And why are alkanes saturated? Because alkanes have single bonds. Alkanes, they possess what we call single bonds. I hope you are following me. And the single bond is the functional group of the alkane. Let me give you guys an example. Let us try to draw the Kekulet structure. The Kekulet structure, the Kekulet structure of an alkene member. For example, butane, which is C4H10. Let us try to draw the Kekulet structure. So it has 4 carbons, right? So you just write 1, 2, 3, 4, right? And it has how many hydrogen? 10 hydrogen. So all you just have to do is to add 10 hydrogen. You see. I hope you are seeing this. So this is very simple. So basically, this is the structure of butane, just ordinary butane. And you can see the carbon to carbon bonds are all single bonds. So that tells you that this is a member of what? Of the alkane family. So now let us move to the IUPAC nomenclature. The IUPAC nomenclature of alkanes. Let us move to the IUPAC nomenclatures of alkanes. The IUPAC nomenclature of alkanes. So, what is the meaning of IUPAC for those that don't know what IUPAC means? IUPAC means International Union of Pure and Applied Chemistry. You can see this in your JAMB exam. Of pure and applied chemistry. That is the meaning of IUPAC. So now, let us do the IUPAC nomenclature or the IUPAC naming of alkanes, right? So now, let me give you guys an example. IUPAC usually have different rules. So let me give you guys an example to name a very simple compound first. Let me write the compound. So if you see it in your JAM exam that you are asked to name this particular alkane compound, the first thing to do if you want to name any compound is to know the functional group of that compound. So now for this particular compound, what is the functional group? the functional group is single bonds. That means that it is an alkane. It is an alkane. So after you know the functional group, what is the next thing to do? The next thing to do is to identify. Let me highlight the rules to identify the longest continuous longest continuous carbon chain. That is the next thing. After you know the functional group, to name an alkane, the next thing is to identify the longest continuous carbon chain. I call it the LCCC, the longest continuous carbon chain. And what does that mean? The longest continuous carbon chain, what does it mean? It means that carbon bonding to carbon in the chain, which one is the longest? That if carbon is bonding to carbon, what is the longest? For this particular example now, let us count carbon bonding to carbon. Let us count it. One, two, three, four. If we count it straight, we will get four, right? One, two, three, four. But also, we can also count it to the top because this is a branched chain. We can also count it to the top, right? One, two, three, four, five. You can see if we count straight, we'll get four. But if we count to the branched side, we'll get five. So now we need to take the higher one because we need the longest continuous carbon chain. We need to take the longest. So this is going to be our carbon chain. One, two, three, four, five. I hope you understand. So after you have done that, the next thing is to identify the substituents. The substituents. Right? You identify the substituents. Now, many people will ask me, what are substituents? So, substituents are attachments. Substituents are attachments to the longest continuous carbon chain that are not hydrogen. Other atoms or other elements that are attached to the longest continuous carbon chain that are not hydrogen, they are called the substituents. You understand? So now you can see that this Br, this is bromine. It is not hydrogen and it is attached to the longest continuous carbon chain. So it is a substituent. This chlorine, it is attached to the longest continuous carbon chain and it is not hydrogen. It is a substituent. This F, fluorine, it is not hydrogen. It is also a substituent. Even this CH3 is also a substituent because it is also attached to our longest continuous carbon chain. So in short, we have how many substituents in this particular question? One, two, three, four. We have four substituents. So let us try to write the substituents out. So I'll just write substituents. So we have bromine. Let us write it out. Bromine. After bromine, we have chlorine. After chlorine, we also have fluorine. After fluorine, we also have methyl. You can see, I told you people alkyl group before. You see, CH3, this is methyl group. You see that it is acting as a substituent. That was what I was trying to explain before. So after you have identified your substituents, what is the next thing to do? The next thing to do is to what? Determine the direction of naming. The direction of naming. You see, this law is very, very simple. Just know this law. To determine the direction of naming. When I say determine the direction of naming, that are we going to name in this direction towards the left, or are we going to name towards the right? Right? That are we going to count like this? 1, 2, 3, 4, 5. Or we are going to count like this. 1, 2, 3, 4, 5. You understand? So how do we know the direction of our naming? You understand? That's the question. How do we know the direction of our naming? The direction of our naming can be known through the positions of our substituents in either directions, right? So let us try to get it. So if you are naming towards the left, let me write it like this. If you are naming towards the left, towards this side, our substituents are on carbon what? If we are naming towards the left, this is going to be our carbon 1, carbon 2, carbon 3, and these are carbon 4, and these are carbon 5. If we are naming towards the left, right? So our substituent bromine is on carbon what? Carbon 5. Carbon 5. Chlorine is on carbon what? The same carbon 5. So right, another 5. Fluorine is on carbon what? Carbon 4. If you are naming towards the left, 4. And methyl is on carbon what? Carbon 3. This is methyl attached to this carbon, carbon 3. Right? So now, if you want to name towards the right, now, if you want to name towards the right, like this direction, this is going to be our carbon 1. This is going to be our carbon 2. This is going to be our carbon 3. This is going to be our carbon 4 and our carbon 5. So now our substituents, bromine is on carbon what? carbon 1, right? Even chlorine is on carbon 1. So we have 1, 1. Our fluorine is on carbon what? Fluorine is on carbon 2, right? This carbon, carbon 2. So you write 2, right? And methyl is on carbon what? This is our methyl attached to carbon 3. If you are naming towards the right, so carbon 3. So now all you just have to do is to sum all of these numbers up, right? If you add all of this together, this is going to give us 17, and this is going to give us what? 2, 4, um, 7. So what you have to do is to follow the smaller one. You need to follow the smaller direction. So 7 is smaller than 17. So in short, we are going to name in the direction to the right. You understand? Most times we usually consider the four substituents, the number or the position number of the first substituent. The position number of this substituent is 5, and the position number of this one is 1. So we have to name in this direction because this is the smallest position number. So in short, we are naming in what direction? We are naming towards the right, right? So now what we need to do now is to be naming. Why naming? We'll name our substituents first, right? We'll name our substituent first with a suffix. You understand? And then we are going to give it a parent name. Now, where will the parent name come from for this particular compound? Don't forget that our longest continuous carbon chain, the parent name will come from the longest continuous carbon chain. Before we identify that our longest continuous carbon chain is what? 5, right? 1, 2, 3, 4, 5, right? And what I taught you before, that a carbon or a carbon atom that is an alkane, we said this is an alkane that has 5 carbon is what? It's called what? 5 carbon is called what? Pentane. Pentane. So our parent name is going to be pentane. But before we write that pentane, we must put all of these substituents there. You understand? We must put all of these substituents there. So I'm using this as an example for you guys to know how to name alkanes. So now we are going to name these substituents in alphabetical order. We need to arrange them in alphabetical order, right? You see, when I was writing the substituents, I was intentional. I already wrote them in alphabetical order. B before C, before F, before M. So it must be in alphabetical order. In your JAMB exam, they might confuse it. So you must ensure that your substituents are in alphabetical order. So bromine. Our bromine is on carbon what? This is our bromine is on carbon 1 because we are naming towards the right. So we are going to write 1 bromo, 1 bromo, 1 hyphen bromo. Then we put another hyphen. We'll move to the next thing. The next substituent is what? Chlorine. Chlorine is on what? Carbon. It's also on carbon 1. Then you write 1 hyphen chloro. So you must put the O suffix there to show that the naming has not end. Then fluorine. Our fluorine is on carbon what? Carbon 2. You put your hyphen 2 fluoro. And then what is the last substituent? The last substituent is methyl. And our methyl is on carbon what? Carbon 3, right? 1, 2, 3. Methyl is attached to this carbon. So 3 methyl, right? 3 methyl. I think that's all the substituents. That's all the substituents we have. So 3 methyl. All we have to do now is to put the parent name. The parent name is what? Pentane. So 3 methyl pentane. So this is the name. 1 bromo, 1 chloro, 2 fluoro, 3 methyl pentane. If you can follow this rule, you'll be able to name any compound that is an alkane. I believe this is very simple to understand. So now let us start with the alkenes homologous series. This alkenes homologous series, they have another name, which is the olefins. So if you see it in your JAMB exam, the olefins are also called what? Alkenes. So that is it. And what is the general formula of the alkenes? The general formula of the alkenes is CnH2n. Unlike alkane, which is CnH2n plus 2. Don't forget this formula. So, what is the first member of the alkane family? One thing that is peculiar about the alkane is the possession of double bonds. The alkane possess double bond, and their suffix is in. Unlike the alkanes, that their suffix is in. You understand? So, the first member of the alkene homologous series is 18. As you can see. You can see the first member of the alkene series is alkane, starting from 1 carbon. But unfortunately, alkene does not have a carbon 1. It does not have a member that starts from 1 carbon, because since it wants to have a double bond, there must be 2 carbons to form at least a single bond, double bond together. So the first member of the alkene series is what? 18, and the formula is what? C2H4, and it is gotten from this formula. Just put 2 here. You have C2, then 2 times 2 is 4. This is 18. So after 18, you have propane, normal, just like our alkane. Just like our alkane. The difference is just you change the A to in. You change the A to E. You understand? So the formula is what? C3H6. Then you go to butene, which is C4H8, and so on and so forth, following the same pattern I give you guys for the alkanes, right? So that is basically it. So let us quickly go into the naming of alkenes, right? So let me give you guys an example, or let us draw the structure of C2H4, which is 18 first. See, this is it. C double bond C, then we have hydrogen, 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 hydrogen. So in short, this is 18. And one thing I told you guys, alkene is an what? Is an unsaturated organic compound. Don't forget that unsaturated organic compounds are compounds that have either double bonds or triple bonds. So alkenes or the olefins, they are an unsaturated organic compound. And there's one thing I want to tell you guys. Maybe I'll tell you guys I missed the video. If you've been enjoying this video, don't forget to subscribe to this YouTube channel, like this video, and comment if you have questions. So let me give us a question so that I can tell you the laws of the IUPAC nomenclature, of the alkenes. You understand? IUPAC nomenclature of the alkenes, right? So let me form a question so that we can work with. You understand? Let me form a question that we can work with. I'm trying to make a question that will be at least, that will be a bit tasking for us to do. So this is it. This is our question. You can see this question is very simple, right? So now, if you want to name an alkene, it is still the same step for the alkene. You need to first know the functional group. The functional group for this alkene is the double bond. If you see the double bond, you see that it also has a single bond, right? But the priority of the double bond overshadows the priority of the single bond. Hope you are getting me. So this is an alkene member. We have known that. After then, you identify the LCCC. That's the longest continuous carbon chain, right? So I'm not going to write that. Identify the longest continuous carbon chain. In this particular compound, the longest continuous carbon chain is straight. It's just 1, 2, 3, 4. 4, right? 1, 2, 3, 4. So what does this tell us? This basically tells us that this particular compound is butene. The parent name is butene because it has how many carbon? 4 carbons. 1, 2, 3, 4. It tells us that this is butene. So we can just write our parent name, or we can say parent chain. We already know that it's butene, right? Butene. So just know it somewhere that it is butene. So now what is the next thing? We identify our substituents, right? What are our substituents here? Things that are not hydrogen, chlorine and fluorine. I think chlorine, fluorine, and then another chlorine here, right? So we have chlorine. Let me just write. We have chlorine times 2. We have chlorine in 2 places, and then we have just 1 fluorine, right? So now, to know the direction of naming, if you are naming towards the right or you are naming towards the left, for alkenes, we don't usually consider the position of the substituents. For alkenes, we consider the position of the substituents to be able to know the direction of naming. But for alkenes, it is not like that. So to know the direction of naming for alkenes, you need to consider the position of the functional group. So you will name in accordance to the position that is closer to the functional group, right? So if you want to name towards the left, if you want to name like this in this direction, our functional group is going to be on carbon what? 1, 2. This is where our functional group is. So it's going to be on carbon 2. This is carbon 2 if you are naming towards the left, right? There's also another functional group here on carbon 3 as well, because there are two functional groups in this one. I'm still going to give us another example that has only just one functional group of a double bond. You understand? So that is that for that. Why, if you want to name towards the right, if you want to go in this direction, our functional group is on this carbon, the first carbon, which is carbon 1. So you need to pick the smallest one. So this is carbon 1. So we are going to pick this direction, which is in the smaller direction. So we are naming in this direction. So let us name with our substituents. We have two chlorine atoms, right? So if you want to name in this direction, this is carbon 1, this is carbon 2, this is carbon 3, and this is carbon 4, right? So our chlorine is on carbon 1 and another one is on carbon 4. So we are going to write 1, 4 dichloro. You can see I added di, showing that the chlorine are 2. We have two chlorine atoms. If it were supposed to be 3, it would have been trichloro. If it were 4, it would have been tetrachloro, and so on and so forth. So after chlorine, we have fluorine. So fluorine is on carbon what? Fluorine is on carbon 4. So 1, 2, 3, 4. Fluorine is on carbon 4. So we write 4 chloro. 4 chloro. Then I want to complete my naming here because there's no space here. 4 chloro. Oh, sorry, it's not chloro, fluoro. Sorry. 4 fluoro. It is fluorine. No. 4 fluoro. 4 fluoro. And then what? The parent name, butene, right? But look at this thing. It does not only have one functional group, it has two functional groups. So we have to say in the name that it has two functional groups. So we cannot just write butene. We are going to write but, right? Are you following me? But, then you put hyphen. We will now say the position of the double bond. The double bond is on carbon 1, then the other one is on carbon 2. So we now say but 1, 2 die in. Hope you get me. Saying that the double bond or the functional group is on carbon 1 and carbon 2, right? So let me quickly give you guys another example that is very simple, a very simple one, the one that you will not get confused at all. So I'm just trying to give you guys difficult ones at first, so that if you see any difficult one in your JAMB exam, it's not going to be difficult for you to answer. You understand? So let us quickly do another one. So this one, mm, okay, I'm trying to form the question for you guys. Sorry, I don't want to. This hydrogen is not there, please. This hydrogen is not there. So let me put chlorine here. And then let me put another fluorine here. And then let me put bromine here. And then let me add hydrogen here and also hydrogen here. I think we are good to go. Yes, we are good to go. So if you see this kind of a question in your chemistry jam exam, how will you name it, right? The first thing is to know the functional group. You can see the functional group is alkene. It's double bond. You see the double bond. It is an alkene. So the next step is to know the longest continuous carbon chain, right? We need to count the longest continuous carbon chain. If you want to count the longest continuous carbon chain, we can decide to count like this: 1, 2, 3, 4. This is 4. But is it the longest? No, it is not actually the longest. So there's another way we can count. We can start counting from this C3H7, which is our propyl, right? So 1, 2, 3, 4, 5, 6, 7. So definitely our longest continuous carbon chain is 7, right? Our longest continuous carbon chain is 7. From this place, 1, 2, 3, 4, 5, 6, 7, right? So we can know that the parent chain at least is what? 10, because it is 7, right? So now the next thing is to identify the substituents, right? The substituents. What are the substituents that we have here? We have bromine, right? So I can just write Br. We have chlorine, right? That's Cl. And what else? We have fluorine. We have two fluorine, right? We have two fluorine. We have two fluorine. So I can just write F times 2. And also, what else do we have? Okay, we have this CH3. This CH3 also, it is a substituent. Because why? Because it is attached to the longest continuous carbon chain and it is not hydrogen. Don't forget that this is the longest continuous carbon chain. from C3H7 going like this, like this, like this, like this here. So this is CH3 is also a substituent. And what is the name of CH3? Methyl, right? So in short, these are the substituents that we have, right? So now let us name it. Now, don't forget that we need to know the direction of naming. Are we naming towards the right or we are naming towards the left? And remember, I told you guys that for alkenes, if you want to know the direction of naming, it is the position of the functional group that will tell you which direction to go, right? So if you want to name towards the left, if you are going towards the left like this, our functional group, this is it. It's going to be on carbon what? Carbon 1, carbon 2. It's going to be on carbon 2. If you are naming towards the left, it's going to be on carbon 2 because this is the double bond. But if you want to name towards the right, if you are naming towards the left, it's going to be on carbon 2. But if you want to name towards the right, it's going to be on carbon what? 1, 2, 3, 4, 5. It's going to be on carbon 5. So which one will we pick? We'll pick the smaller one, which is carbon 2. So we are going to be naming towards the left. So this is going to be our carbon 1, our carbon 2, our carbon 3, and our carbon 4. Then 5, 6, 7. You understand? So let us start naming. Our bromine is on carbon what? Is on carbon 1. So we have something like 1 bromo, right? Then our chlorine is on carbon what? It's also on carbon 1. So 1 chloro, and then we move to fluorine. We have two fluorine atoms. One is on carbon 2. This is its fluorine. One is on carbon 2 and the other is on carbon 1, right? So we have something like 1, 2 dichloro, 1, 2 difluoro. You understand? I hope you guys are following me. 1, 2 difluoro, 1, 2 difluoro. Then we have methyl. Methyl is on carbon what? Methyl is on carbon 3, right? 1, 2, 3. Methyl is on carbon 3. So 3 methyl. Then we'll put the parent name. The parent name is heptene, right? But we cannot just write heptene. We need to let them know the carbon that is bearing the functional group. And that is carbon 2. 1, 2. This is the carbon that is bearing the functional group. So we'll just write hept, hept 2 in. You understand? So hept 2 in. So the name is 1 bromo, 1 chloro, 1 2 difluoro, 3 methyl hept 2 in. I believe this is very simple to understand. So you guys should try solving more questions on this. And also you can check my page. I have solved many IUPAC nomenclature questions here on my TikTok channel. Sorry, here on my YouTube channel. So you can also check them out and also learn from them. So now let us move to the alkynes. Let us move to the alkyne homologous series. Now for the alkyne homologous series, it is not difficult. It follows almost the same rules as the alkane homologous series, right? So the formula for the alkyne homologous series is what? CnH2n minus 2, right? CnH2n minus 2. This is the formula for the alkyne homologous series. And the first member of the alkyne homologous series is ethyne. Ethyne. The first member of the alkyne homologous series is ethyne, and the formula is C2H2. C2H2. And this formula is gotten from this formula, right? So if you put N, if you replace N with 2, right, you are going to have C2, then H2N, right? 2 times 2 is what? 4. 4 minus 2 is 2. So ethyne is C2H2. So let us try to draw the structure, right? So it has, and don't forget one thing about ethyne is that ethyne has triple bond, and ethyne is also an unsaturated organic compound because it has triple bond. So this is for ethyne. You can see this is the structure. Very, very simple. C2H2. So the second member is what? The second member is propine. The second member is propine, and that is what? C3H4. The third member is what? Butane, and that's what? C4H6, and so on and so forth. So it is just its own suffix is yne, YNE. That is the suffix of the alkyne homologous series. I hope you are following me. This is very simple to understand. So now let me give you an example of a naming that is about the alkyne. So this one is, it follows the same rule as the alkene, right? So let me give you guys an example. Right? So let me give you guys an example. Okay, so you guys should wait. Okay, so this is the example. Here we are. Here we are for the example. Let me put bromine here. So now, to name this particular compound, first thing is to know the functional group. And you can see the functional group is the triple bond, right? So it tells us that it is an alkyne. After that, you determine the longest continuous carbon chain. Here, the longest continuous carbon chain is just a straight chain, right? It's just a straight chain. Or let's not make it a straight chain. I don't like straight chain like that. Let me make it a bit complex. C2H5. So I'm not making it a straight chain again. I edited this place. So our longest continuous carbon chain is going to be what? 1, 2, 3, 4, 5, 6, 7. Why I'm doing this is just to let you know that every time is not the longest continuous carbon chain, every time is not always the straight chain. Sometimes it can be straight chain, sometimes it can be branched chain. So don't get confused, right? So the longest continuous carbon chain is 1, 2, 3, 4, 5, 6, 7. So 7, that tells us that the parent name is what? Correct. That tells us that the parent name is what? Heptine. Heptine. So now the next thing is to know the substituents, the attachments to the longest continuous carbon chain that are not hydrogen, right? We have bromine, our subs, we have bromine. How many bromine? Two bromine self. This one and this one, right? We also have chlorine, and also we also have fluorine. F. I think that's all, yeah. So now the next thing is to know the direction of naming. Are we naming towards the left or we are naming towards the right? This follows the same rule as the alkane. We will choose the position number that is closer to the functional group. If you want to name towards the right, like this, the functional group is on carbon, this carbon. So it's going to be 1, 2, 3, 4, 5. It's on carbon 5. If you want to name like this. But if you want to name in this direction, towards the left, the functional group, this is the functional group is on carbon 1, 2, is on carbon 2. So we'll name towards this direction. So this is going to be our carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and this is going to be our carbon 6 and 7. Right? I believe you guys get me. So now, our first substituent is bromine. Our bromine is on carbon 1. This is bromine is on carbon 1. Another one is also on carbon 5. So we have something like 1,5 dibromo 1,5 dibromo, and then we move to chlorine, right? Chlorine is on carbon what? Carbon 1. 1 chloro, 1 chloro, and then fluorine. Fluorine is also on carbon 1. So we have 1 fluoro also. 1 fluoro. Then we put our parent name, which is heptine. But we need to let them know the position of the triple bond. And the triple bond is on what? Carbon 2. So it's going to be what? Hept, hept 2 ine. It's going to be hept 2 ine, right? So I believe this is very simple to understand. The name is 1,5-dibromo, 1 chloro, 1 fluoro, hept 2 ine. So let us move to another homologous series. And this is going to be the last homologous series for this particular video. And then we'll complete everything in the part 2. So the next homologous series for today is the homologous series of the Alkanols. The homologous series of the Alkanols. This is very simple. So what is the formula or the general formula for the Alkanols? The general formula for the Alkanols is what? ROH. This is the general formula for the homologous series of the alkanols, right? The alkanols are also called the alcohols, right? The alcohols. So this is it basically, right? Now let me tell you, this R that I wrote here, what does it mean? This R represents an alkyl group or an aryl group, right? An alkyl group or an aryl group, right? So I believe you all know what an alkyl group is. I've explained earlier. An aryl group is like an aromatic compound, like a compound of benzene. Those are aryl groups. But mostly in your this thing, mostly in your JAMB exam, they will usually give you alcohol that have aryl groups attached to them. You understand? So now let us continue. The first member of the alkanol is the methanol, 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 right? And the formula of methanol is what? CH3, our normal methyl. You first write your methyl because this is methanol. You know the vibe now. Methyl. Then you put your OH. So what is the second member? The second member is ethanol. Ethanol. Who can guess it? Correct. It's correct. So you put your ethyl, then you write OH. C2H5, then OH. You can see the next member is propanol, right? All you just have to do is to put your own normal formula now for propyl first. C3H7, then add OH. Next one is butanol, butanol. Put your normal butyl formula, which is C4H9OH. Just like that, like that, like that, like that. That's how it goes. You go to pentanol, hexanol, and the rest. So for this alkanol, you can see that it is organic chemistry is very simple. If you've not subscribed to this YouTube channel, now is the best time to subscribe. I hope you understand all of these things. So now let me give you guys the structure of, let me use methanol as an example to show you how the structure is. So now methanol, let me draw it for you. C is the central atom, right? C is the central atom. So we have C, then H3. Okay, I'm drawing the Kekulet structure. This is what we call the Kekulet structure. Then attached to OH. You can see. Can you see? So this is the structure of methanol. This is how it looks like. You can see that oxygen is taking two bonds. Oxygen is taking two bonds. You know, at the beginning of this video, I explained why um carbon usually take four bonds. So now for oxygen, why does oxygen take two bonds? This is not part of the lesson, but let me just explain. You know, the oxidation state of oxygen most times is O2 minus, right? That's the valency, that's the oxidation number, right? So let me explain why the oxidation number is minus 2, and that's why it takes two bonds. Because the atomic number of oxygen is 8, right? And in the first shell of oxygen, it will have 2 electrons, right? And in the second shell, it will have 6 electrons. And don't forget that I told you guys that this is the second shell. The maximum number of electrons that can be in the second shell is what? 8, correct? So how many electrons does it need more to complete octet? 2 more. So it can actually collect that 2 more from another atom. Understand? It can collect it from another atom, or mostly in organic compounds, it's usually bond covalently. It shares it with another atom. You understand? So it just takes 2 bonds to share, and that is why oxygen takes 2 bonds. So this is the structure of methanol. Let us try to draw the structure of ethanol. Ethanol is C2H5. This is very simple. Just write your C to C bond, C to C bond, then add your H, add your H, add your H. You see, this is our C2H5. Then you just have to add your OH. That's all. So this is the structure of ethanol. This is the structure of ethanol. Now let us move to the naming of alkanols, the IUPAC nomenclature of alkanols, right? So now I'm going to tell you the law of the IUPAC nomenclature of alkanols. It is very simple. It is more or less like the alkenes and alkynes, right? Let me just give you guys some simple examples, right? I'm giving you simple examples now. So if you can solve all of these questions, then your JAM exam is going to be very easy for you to do. It's going to be very easy for you to do, right? So this is a question to solve. Fluorine, let me put chlorine, and let me put bromine. Right. So this is a question that we can solve, right? So now, if you check this question very well, anytime they ask you to name anything, I usually tell you that the first thing to do is to know the functional group. In this particular place, we all know that this is somehow like an alkane. But what is the difference? OH. This has an OH group. The priority of OH group is higher than the priority of alkane. So the OH group here we take the functional group. So this is telling us that this particular compound now is an alkanol. That is what it's telling us. This particular compound is an alkanol, right? So after we have known that, after you have seen your OH, that you have known that this compound is an alkanol, the second thing is to what? Identify your longest continuous carbon chain, which I call your LCCCC. So now let us try to identify our longest continuous carbon chain, right? If you count like this is C3H7. 1, 2, 3, 4, 5, 6, 7, right? This is 7. Okay, let us count another way. 1, 2, 3, 4, 5. This is 5. So if you can see, there are two ways of counting. we have one is 7 and one is 5. So which one is longer? We need to pick the one of 7 because 7 is longer, right? So 1, 2, 3, 4, 5, 6, 7. So basically, we know that our parent name is 7, right? And if it is 7, then what is going to be our parent name? I'm waiting for your answer. What is going to be our parent name? Correct. Our parent name is going to be what? Heptanol. Our parent name is going to be heptanol. You can see that the suffix is "-ol". You can see, just like alkanol. That's one thing you need to know about the alkanol. The suffix of the alkanol is "-ol". All. Don't forget. Don't forget that. You can see, as in methanol, as in ethanol, as in propanol, butanol, and all of those. So now we have identified that. We have known that our longest continuous carbon chain is 7. 1, 2, 3, 4, 5, 6, 7. Right. So the next thing is to identify our substituents, right? Our substituents. People should not forget that I usually tell you people that substituents are attachments to the longest continuous carbon chain that are not hydrogen, right? So this is our longest continuous carbon chain from C3H7 to this carbon. So what are the things that are attached to it? Bromine is attached to it, right? Bromine is attached to it. Bromine. So we can write bromine, Br. Then also chlorine is also attached to it, right? Chlorine is also attached to it. Cl. Also, what is also attached to it? Um, C2H5 is also attached to it. Okay, we have two chlorine atoms, this one and this one. So chlorine times 2. Also, what else? We have fluorine also. We even have C2H5. C2H5 is what? Ethyl. So we have ethyl. And also, we also have fluorine, right? We also have fluorine. So we can write fluorine. Let us just write F for fluorine, right? So we have 1, 2, 3, 4. This one, 5 substituents. So now, what we need to do is to know the direction of naming. Are we naming towards the right or we are naming towards the left? Are you following me? So now, just like the alkenes and the alkynes, the naming of alcohols is also dependent on the position of the functional group. This is the functional group. So the position number that is closest to the functional group will determine how we are going to name it, or we determine the direction, right? So if you want to name towards the right, this way, right? Our OH group is on carbon what? 1, 2, 3, 4, 5, 6 is on carbon 6. But if you want to name towards the left, our OH group is on carbon what? 1, 2, it is on carbon 2. So basically, we are going to follow the smaller one, carbon 2. So we are following this direction. So now let us name our compound quickly. So bromine. Our bromine is on what? Is on carbon 1. So let us just number this 1, 2, 3, 4, 5, 6, 7, right? So bromine is on carbon what? Carbon 1. So we have something like 1 bromo, 1 bromo. Then after bromo, what else do we have? Chlorine. We have 2 chlorine atoms. One is on carbon 1 and the other is on carbon 4. So we have something like 1, 4 dichloro, right? 1, 4 dichloro. You can pause this video to solve it. You can pause this video to name it. And when you finish naming your own, you can come back to come and check. Dichloro. Then we move to ethyl. Ethyl is on carbon what? Carbon 3. 1, 2, 3. Our ethyl is on carbon 3. So 3 ethyl, 3 ethyl. Don't forget that you must arrange this in alphabetical order. You see, when I wrote my substituents, I intentionally arranged them alphabetical order. B came before C, C came before E, and E before F, right? So then we move to fluorine. Fluorine is on carbon what? Carbon 1. So 1 fluoro, 1 fluoro. Then we put our parent name. Our parent name is heptanol, right? But we cannot just write heptanol. We need to show, or we need to show the position of the OH group or of the functional group. The functional group is on what? Carbon 2. So we just write hept, right? Hept 2 or hept 2, or we write heptan 2 or, right? Heptan 2 or heptan 2 or, just like heptanol, heptan 2 or. So the name is 1 bromo, 1 4 dichloro, 3 ethyl, 1 fluoro, heptan 2 or. Imagine if we had 2 OH groups here before, it could have been 1 fluoro, heptan 1 2 di or, right? So now for this alkanol, I want to teach you guys something about the alkanol family. I want to teach you guys something important about the alkanol family, and I don't want you guys to take that in for granted. The alkanol family actually have classifications. The alkanol family have classifications, right? Let me explain. We classify the alkanol group into primary, alkanols, primary alkanols, primary alkanols, secondary alkanols, secondary alkanols. The JAM likes asking this thing. Secondary alkanols and tertiary alkanols. Tertiary alkanols, right? So, how do we know the differences between each of these level of alkanols? Now, before I explain this thing, let me explain something. There is something we call the alpha carbon. The alpha carbon. Now, what is the alpha carbon? Let me explain. The alpha carbon, it is the carbon that is bearing the functional group. That's what we call the alpha carbon. You understand? The alpha carbon is the carbon that is bearing the functional group. Or most times the alpha carbon in different ways. We define alpha carbon as a carbon that is attached to three different types of atoms. But in this place, we can call our alpha carbon the carbon that is bearing the functional group. In this OH now, let me give you an example. In this one that we just named, no, we just named this now. The alpha carbon is this carbon. Why? Because this carbon is carrying the functional group. And also, if you check this very well, this particular carbon is attached to three different types of compounds. Attached to this is different from this is different from this, and this is even different from this. So this carbon is the alpha carbon because it is bearing the functional group, right? So that is the meaning of alpha carbon. Alpha carbon is a carbon that is bearing the functional group, or a carbon that is attached to four different types of atoms or compounds. You understand? That is the alpha carbon. Now, I want to tell you guys something that is very simple. Primary alkanol. Primary alkanols are alkanols that have only one alkyl group attached to the alpha carbon. So, are you guys following me? I said the primary alkanol is the type of alkanol that has only one alkyl group attached to the alpha carbon. So, let me give you guys an example of a primary alkanol. For example, this is an example of a primary alkanol. This is an example of a primary alkanol. See now, what is the alpha carbon in this case? This is the alpha carbon, right? Let's say this is the alpha carbon because it is bearing the functional group. Or you just say that primary alkanol or the alpha carbon is the carbon that is bearing the functional group. So primary alkanol is an alkanol that the carbon that is bearing the functional group is only attached to one alkyl group. So this is the carbon that is bearing the functional group, and it is attached to just one alkyl group, which is this, which is CH3. You can see CH3. So this is a primary alkanol. It is attached to hydrogen. Hydrogen is not an alkyl group, but this CH3 is an alkyl group. CH3 is an alkyl group. So this is a primary alkanol. Why? Because it is attached to only one alkyl group. So now for secondary alkanol is a type of an alkanol where the carbon that is bearing the functional group, or what we call the alpha carbon, is attached to two alkyl groups. For example, let me give you guys an example. A very, very simple example. That's what I want to give you. So that you understand the concept very well. See now, this particular one, what is the alpha carbon in this case? This is it, this one, because it is this one that is bearing the functional group, right? Or the carbon that is bearing the functional group in short. You understand? This is the carbon that is bearing the functional group. So this carbon that is bearing the functional group is attached to two alkyl groups. This one, this CH3, CH3, and this other CH3. You can see. And it's also attached to hydrogen. Hydrogen is not an alkyl group, so it is not counted, right? So a secondary alkanol is an alkanol that is attached to two different alkyl groups. So now for tertiary alcohol or tertiary alkanol, guess correct. Tertiary alkanol has three alkyl group attached to the carbon bearing the functional group, right? So let me give you guys an example. Let me say this is OH, this is CH, CH, H, H, H. This is CH3. Let me just say this is C3H7, right? So in this case, what is the carbon that is bearing the functional group? This carbon is the one bearing the functional group, right? So it is attached to three different alkyl groups. It's attached to this propyl, you can see, attached to this propyl. It's also attached to this methyl, which is CH3, right? It is also attached to this C2H5, right? It is also attached to this C2H5. So the tertiary alkanol is an alkanol that is attached to, it is an alkanol that the carbon bearing the functional group is attached to three different alkyl groups or to three alkyl groups. I believe that is very simple to understand. So let me teach you guys another thing under the classification of alkanol. There is another classification of alkanol which we call the monohydric alcohol or the monohydric alkanol, the monohydric alkanol, the dihydric alkanol, the dihydric alkanol. I'm saying all of these things because JAM usually sets questions from them. And also the trihydric alkanol, right? So this is very simple. To know this one is very simple. A monohydric alkanol is an alkanol that only has one OH group. While dihydric alkanol is an alkanol that has two OH groups, right? And trihydric alkanol is an alkanol that has three OH groups, right? You see, this one is very simple. So monohydric alkanol, for example, now this example, all of these examples that I gave, they all have one OH group, one OH group, one OH group, one OH group. All of these are all examples of monohydric alkanol, right? Because they only have one OH group, right? So let me give you guys an example of a dihydric alkanol. A dihydric alkanol is an alkanol that has three OH groups. Dihydric is two OH groups. So you have something like this. I just want to give you a quick example, right? So this is a dihydric alkanol. This is a dihydric alkanol. And if you were to name this alkanol, how will you name it? It is very simple. Actually, this alkanol is very simple. This is actually ethanol. This is ethanol, but this is ethan 1,2-diol. This is, let me write the name. This is ethan. Sorry, this is ethan 1,2-diol. Because why? This is only two carbons and it has two OH groups. So we need to say 1,2-diol, showing that the OH groups are two, right? So this is an example of a dihydric alkanol. Hope you are following me. So now let us go to trihydric alkanol. Trihydric alkanol is an alkanol that has three OH groups. Let me use the the simplest one. Concept. 1, 2, 3. OH. OH. You can see this has three OH groups. So this is an example of a dihydric alkanol. This is an example of a dihydric alkanol because it has three OH groups. And if you were to name this particular trihydric alkanol, how will you name it? It is very simple. Count the number of carbon, 1, 2, 3, right? That shows us that the parent name is propanol, right? Propanol. So you just have to say the position of the OH groups. That's 1, 2, 3. So the name is propan 1, 2, 3, tri-ol. You can see this is very, very simple. You can see it is very, very simple. If you've not subscribed to my YouTube channel, now is the time to subscribe to my YouTube channel. I hope you've been gaining from this particular video so far. So now in the next class or the part 2 of this particular class, we are going to be treating the other homologous series. We are going to be treating the carboxylic acid. We are going to be treating the ketones. We are going to be treating the alkana or the aldehyde. We are going to be treating the esters or the alkanoids. And we are also going to be treating the ethers or the alkoxy alkanes for our next class or for my next video, which is going to be the part 2 of this organic chemistry lesson. If you've gained something from this class, don't forget to say it in the comments. And if you have any questions, you can send everything in the comments and I'll attend to them. So now I want to give you guys a simple work to do. Let me give you guys a simple work to do. It's going to be simple and I want you guys to tell me your answers in the comments just to name it. Now, wait. I want to tell you guys something. People should not leave. This is something that JAM usually sets inside JAM exam. And that is test for saturated and unsaturated unsaturated um, organic compounds. The test for saturated and unsaturated organic compounds. So I told you guys that saturated organic compounds are one that have just single bond, while unsaturated have double bonds or triple bonds. So now, how can we distinguish between these two types of organic compounds? We usually distinguish between them using bromine water, which is reddish brown, bromine water, which is reddish brown, and also we usually use KMNO4, KMNO4. I think the color of KMNO4 is purple. Yes, KMNO4 is purple. So now, for saturated um for saturated organic compounds, they don't decolorize bromine water. You see, they don't decolorize it. They don't decolorize it. They don't decolorize, right? They don't decolorize it. That means they don't bleach it, right? Decolorize. So the saturated hydrocarbons, they don't decolorize bromine water and even KMNO4. But the saturated hydrocarbons, they decolorize it. So if you see this in your JAM exam, you might not see it directly. They can just say 18. If 18, if let me say, if a solution of 18 is mixed with bromine water, what will happen? So you should know that it will decolorize it because 18 is an unsaturated organic compound. So saturated organic compounds, they don't decolorize bromine water and they don't also decolorize KMNO4. But unsaturated organic compounds decolorize both bromine water and KMNO4. People should know all of these things because they are quite important in your JAM exam. If you've not subscribed to my YouTube channel, go and subscribe and click on or turn on the notification bell so that you know when I upload the part 2 of this particular video, organic chemistry part 2. So that's it. For those people that would love to join my tutorial, I have a JAM tutorial which I do for JAM science students, where we teach chemistry, physics, mathematics, use of English, and biology for JAM science students. If you wish to join this class, you can send me a DM on WhatsApp. I'll drop my phone number, right? I'll drop my phone number. You can send me a DM on WhatsApp. And the class is not free. It is 1,000 naira for one subject per month, 2,000 naira for two subjects per month, 3,000 naira for three subjects per month, and 4,000 naira for four subjects per month. I believe this is very simple to understand. And I will see you guys in the next one. Peace out.